Hi, and welcome to 13.2 period and frequency. I kind of said this in the last video, but sometimes I do period and frequency first, so you'll see it as 13.1 period and frequency, because I like to talk about simple harmonic motion. We'll talk about that quick in case you're confused by that. And then I go into wave properties because waves are an example of something that is in simple harmonic motion, but you could have other things that are in simple harmonic motion, but we typically talk about waves the most. You could also have a pendulum. That's another example of something in simple harmonic motion. So typically I do like this lesson first. This would be 13.1. Talk a little bit about simple harmonic motion. Don't go too crazy with it. And then we spend like the whole rest of the year in waves. So if you're super confused by what the heck is simple harmonic motion, well, just listen to this short explanation, I guess. We'll go through the PowerPoint slide, a couple of the slides. Simple harmonic motion, sometimes you'll see it abbreviated SHM, not shake my head, SMH, SHM. The definition is a vibration about an equilibrium position. And remember, I said equilibrium in the last video. A vibration around an equilibrium position in which a restoring force is proportional to the displacement from equilibrium. Fancy definition. Now, examples could be a swinging pendulum or a spring that's vibrating up and down. And it says, what are the restoring forces in these different examples of simple harmonic motion? So the pendulum goes back and forth because of gravity, and the spring goes up and down because there's some spring force. So then there's like some complicated stuff over here. Just focus on the spring for now, I guess. So this dotted line represents the equilibrium position. When the spring is this long, it's happy. It's not too stretched out. It's not compressed. But the further away you get from equilibrium, the stronger the spring force. We learned Fs equals Kx, the stiffness of the spring and the distance from equilibrium. So the bigger X is, the stronger the force is going to be. And that's what they're talking about, how it's proportional. So the force is proportional to the distance from equilibrium. The further away you are, the bigger X is, the stronger the force is. And if that is true, then you have yourself simple harmonic motion. It has to be like a proportional thing. So we could see pretty clearly with the spring how the further away from equilibrium you get, the stronger the force is. And then it's going to cause you to like do this back and forth motion. The force is pulling you towards equilibrium. And here the spring is pushing you towards equilibrium. So that's why it goes back and forth. And then I said for the pendulum, here's our pendulum. How does gravity make the restoring force? And if it's supposed to be proportional, does that mean gravity is changing? Well, if you break, this is the gravitational force. That stays the same. But as this rotates and the angle becomes bigger, you'll notice that, yeah, the gravity stays the same. So I tried to draw that the same size. But the components of the gravitational force change. The components change. So this is FGX. And this is bigger than this tiny bit. And when it's right in the middle, there is no X component of that weight. It's all acting in the Y direction. So in the middle, in equilibrium, this FGX is equal to 0. And it increases the further away you get. And that's simple harmonic motion. The further away you get, the greater the displacement, the stronger the restoring force is. They're proportional, the distance and the force. All right, so that's simple harmonic motion in a nutshell. We don't have to get too crazy into it. You could go super fancy, like, I don't know, man. It's kind of cool, I guess, if you're into that type of thing. But the reason I like talking about it is because you start talking about period and frequency. Now, we talked about period before when we did we did period before when we did circular motion. So here's an example of circular motion, the earth rotating. That's like circular motion. You're moving in a circle right now because you're moving in a circle around the axis of rotation of the earth. And you're also moving in a circle around the sun. So those are just two random examples of circular motion. And we did talk about period when we talked about circular motion. So let's make a connection here. Is circular motion simple harmonic? You could have a period, and I didn't mention it before, but for simple harmonic motion things, you also have a period, right? The period of time it takes to do one cycle, one back and forth, that's one cycle. How much time did that take? That's the period. All right. So you had the period of rotation. So does that mean that it's simple harmonic? No, it's not simple harmonic because you don't go back and forth through an equilibrium position. That's very important, this equilibrium position. All right, you're not like rotating one way and then rotating another way. No, so here, back and forth, back and forth. That's simple harmonic. When it's just a circular motion, you could have number of cycles, number of revolutions. You could have a period. You could even have a frequency, how many revolutions per second. But it's not simple harmonic. So I don't know. Another like fancy thing that I guess is important, period. So let's talk about period and frequency. So that's simple harmonic motion. We're done with that craziness. What is the difference? So this is a review. You should know this already. Period is the time it takes for a complete cycle. Just one cycle. How many seconds does it take to do one cycle? And we made up this formula. If they tell you it takes 6 seconds to do 2 cycles, what's the period? You just do 6 seconds divided by 2 cycles. And you get a period of 3 seconds. That's super important. How much time does it take for one cycle? 3 seconds. That's the period. I like to say it's the period of time. Right? That's a saying. People say that. What's the period of time it takes for a complete cycle? How many seconds for one? What we didn't talk about was a closely related thing called frequency. So the definition of frequency is not the time it takes for one cycle, but the number of cycles per second, or the fancy way to say it, the number of cycles or vibrations per unit of time. Notice the units here. Seconds, inverse seconds. The -1 power means 1 over s. But that's a weird way to write a unit, not 1 over s. So they just, hey, let's name it after this dude Hertz. Okay? So H, uppercase H, lowercase z, instead of an inverse second, you could write a Hertz. Both are valid units for frequency, but just write Hertz. You know what happens when people forget the unit for frequency? That really hurts. That really hurts my feelings. You get it? It hurts when people forget the units. Oh man, I'm going crazy. Not really. So the period, we had an equation. It's the time per number of cycles. The frequency is the number of cycles per time. So if we wanted to say, let's use our example from before. We said we did 6 cycles. We did 2 cycles in 6 seconds. The period is 3 seconds. What's the frequency? So you would do, what did we say? 6 seconds and 2 cycles. And you could see how the units become cycles per second. All right, so this becomes 1 over 3. You could say 1 over 3 inverse seconds, but that looks weird. So we're going to do 1 over 3 hertz, or 0.33 hertz. And what this is saying is you do 1/3 of a cycle in 1 second. If you give me 1 second, I'll only get through 1/3 of my whole cycle. I'm not going to do a full cycle for you. So that's kind of like, it's a low frequency. You could have frequencies of certain simple harmonic motion things or waves that are like 600 hertz, 300 hertz, 6,000 hertz. It depends on what kind of thing you're talking about. Are you talking about a sound wave? How many waves per second would a sound wave have? And then electromagnetic waves. How many electromagnetic waves per second? It becomes a lot more. Typically. So you probably saw it. So talking about these equations are not in your reference table. You want to know what the equation is in your reference table? It'd be nice to have all 4 of these. This is on this slide over here. Oh my gosh. This was on this slide over here. Okay. But the one they give you, if you look in your reference table, it's only this. Oh my goodness, what happened to my pen? Okay, this is the only one they give you in your reference table. Do you have to write this one in? Probably not, but I recommend writing these 2 versions in your reference table so you don't forget. Okay. Oh, I did want to say one thing. So yeah, so the period is the period of time it takes for a complete cycle. The frequency is, you could think of it, how frequently are the waves happening? Is it a lot? Is it a little? In this case, it was only a third. It's happening with a frequency of 1/3 of a cycle per second. All right, that's how frequently the waves are going by you. So we could look in our reference table. Let's look in the reference table. All right, so where would period and frequency be? Not on the first page. They talk about like frequency over here, but that's not really the formula that we're looking for. We'll get there. This is electromagnetic waves. So that's unit 15. This is all unit 16 stuff, modern physics. We did electricity. This whole page is electricity. Okay, here we go. So waves. Waves. What page is this? Page 5. Waves. What do they tell us here? Okay, this is I'll give you like a little sneak preview. This is the wave speed equation, and you can see frequency is involved. So first we're going to do, here's the equation that I told you is in the reference table. If you could write the formulas, so the one for period, the time per number of cycles, and then if you want, you could even write the units. The units for period is seconds, and then the made-up equation for frequency. You take the number of cycles and divide it by the time it takes for those cycles to go by, and it'll tell you how much time it takes for one cycle to go by. Oh no, that's period. How many cycles go by in 1 second? That's the unit. So the units is like an inverse second or a hertz. Gets a little confusing. But they're inversely related. You could see because you just take the inverse and then it flips. Like this fraction is just flipped like that. So that's why we say it's inversely related. Okay, I think that's about it. Let's go back to the homework. So the homework will talk about simple harmonic motion first, and then we'll get into some more period and frequency things, which would lead us into tomorrow's thing with wave speed, because you need to know the frequency, and then you need to know the wave stuff, and then we'll do the wave speed. So number 1, the time required for an object undergoing simple harmonic motion to complete one full cycle is called its what? So the time it takes for one cycle is the period of time for one cycle. How many seconds? Number 2, which word describes the number of cycles that can be completed in a unit of time, such as a second? So how many cycles can you do in a second by an object undergoing simple harmonic motion? In other words, how frequently are these waves going by? Is it 60 waves per second? How frequently is it happening? That's the frequency. Number 3, as a pendulum undergoing simple harmonic motion moves away from equilibrium position, the restoring force increases. And I kind of said it before. Sorry if you skipped the beginning, that's totally fine. Track back to where I was talking about pendulums, and I drew this craziness. So anywhere you see this on the YouTubes when you're tracking through, all right, that kind of explains that concept. Oop, that's not what we're doing. We're over here. Number 4, use the diagram to the right. So this is a review of Unit 8 about energy. Just because we're talking about pendulums, so might as well. The kinetic energy is at its maximum value when it's moved. Remember, kinetic energy, movement. If it has velocity, it has kinetic energy. So where is it moving the fastest? Point C. Remember, it's going super fast here, and then it slows down to a stop over here. Okay? So if the kinetic energy is at a maximum over here, all that kinetic energy gets transferred to potential energy over here at position A. And the velocity is at a maximum at C, like we said. And the okay, so where is the acceleration at a maximum value? You could think of this 2 different ways. Acceleration is your change in velocity. So where's your velocity changing at the fastest rate? But then also don't forget Newton's second law, which says that the acceleration is directly proportional to the force and inversely proportional to the mass. So that tells me that wherever the force is the greatest, the acceleration is the greatest. So we're looking for some place that has a very large force. And we talked about how the x component of the force is 0 at point C, but it's the greatest, all right, at point A. And also at point A, your velocity is changing from a velocity going this way, and then the velocity is 0, and then it changes over here. So your acceleration is the greatest at point A for two regions. Where's there a combination of kinetic and potential energy? That's going to be at B, because you are some height above, so there is some potential energy, but you're also moving, so you do have kinetic energy at point B as well. Okay, so number 5, a dog's tail wags 50 times in 40 seconds. What's the frequency, and then what's the period? So if we were going to do the guess method, what information are they telling us? They're telling us a time of 40 seconds, and we could say this is like the number of cycles is 50 cycles. Okay, and they're asking what is the frequency. So use that equation that we wrote in our reference table. The frequency is the number of cycles per second, per time. Okay, or if you wanted to write an equation, you could do like number over t. If you want, if that makes you feel happy, you could do that. 50 divided by 40, and you get 1.25. What are the units for frequency? Well, you could see this is like a number per second, so you could do 1 over seconds. But that's not really what we use. What do we use? What are the units for frequency? When people forget, it really hurts. Hertz. All right, HC. Okay, so letter B. B says, what is the period of vibration? So you could use our like made up formula, but you could also take the inverse. So T equals 1 over F. And then you just plug in what we just found, and you get 0.8 seconds. Okay, so what the heck does this stuff even mean? We're talking about a dog's tail wagging back and forth. So if this is the dog, that's a very nice dog, and the dog's tail is wagging back and forth, and I just realized it's going to be hard to make it go like left and right. So let's say the dog is just as weird as it looks, and it wags its tail up and down. So it starts here, then it goes down, and then it goes back up again to its starting position. That is one time. That is one cycle. So from up, down, and then back up to the starting position. That's one full cycle that we're talking about. Beautiful drawing. I know it makes it super clear. So what does that mean? For the period, it takes 0.8 seconds. You could time it. It takes 0.8 seconds for that dog's tail to go back and forth and back to the starting position. So one full cycle, 0.8 seconds. And if you were also timing it and you were like counted up the number of cycles that the dog could do in 1 second, the dog could do 1.25 wag. So it'll do a full wag and then a quarter of a wag in 1 second. That's what the frequency means. 1.25 inverse seconds, 1.25 hertz. Similarly, now we got Tarzan swinging back and forth on a vine like a pendulum. He's swinging back and forth 3 times in 9 seconds. So we'll write the given info. The time is 9 seconds. You get 3 cycles. And it says, what is the period? And then let me guess, what is the frequency in hertz? Okay, so you could write the period formula. And then you realize they don't tell you the frequency. So you have to do the made up period formula that you hopefully wrote down. And then you could plug in T is equal to 9 seconds divided by 3 cycles. So it takes 3 seconds for one swing. So 1, 2, 3, there and back. And then the frequency is just 1 over the period. You could also do number of cycles per time. You'd get the same answer. So it's the inverse of the period. So this is equal to 0.3 repeating hertz. So if you had only 1 second, you could do 1/3 of a swing. Number 7, while sitting in a boat, a fisherman observes that 2 complete waves pass by his position every 5 seconds. So waves are also simple harmonic motion. And you could count the number of cycles per time. So the time is 5 seconds. and there's 2 waves, so you could do the same process. 2 cycles. Well, you know what? Let's start calling it waves. 2 waves. 2 cycles. They up a crest, a trough, and back to a crest. Okay, the whole thing, the whole wavelength. So what is the period? That's going to be the time per number of cycles. So you could write it like that if you want. Over 2. So period is equal to 2.5 seconds. It takes only 2.5 seconds for one wave to go by. And the frequency is the inverse of that. 1 over 2.5 or 2 over 5. So the frequency is equal to 0.4 hertz. Sorry, I got distracted because I realized I didn't write my formula. What the heck? All right, so you got to make sure you're writing the formulas. I'm a bit out of practice, I suppose. So again, review. It takes 2.5 seconds for one wave to pass by the dude, and then it takes 0.4 hertz. It's going at 0.4 hertz, so that means that you could get 0.4 of a wave in 1 second. You only get 4/10 of a wave pass by if you only have 1 second. You only see a part of the wave, not a full wave. All right. Now, 8. If the frequency of a pendulum is tripled, what will happen to the period of the pendulum? Will it increase or decrease? By how much? Does the period stay the same? All right, so we know that frequency and period are inversely related. And you could write it either way. Now the frequency is being tripled, so let's see what happens. If I triple the frequency here, I just put a 3 in the denominator on this side of the equation. So to make it equal still, whatever I do to one side, I have to do to the other. So I have to take my period and divide it by 3 in order to have this relationship still be equal. So if the frequency is 3 times as big, the period is 3 times as small. It's an inverse relationship. And how can we make this make sense? So if the frequency is 3 times bigger, that means you get triple the number of waves. You get triple the cycles in only 1 second. So the number of cycles that are happening in 1 second is going to triple. So what does that look like in your mind? It's got to speed up, right? If there's triple the number of cycles per second, it's going faster now. And if it's going faster, that means it takes less time. The period is decreased. It's less time for one cycle. Okay? So that's kind of the idea with number 8. And that's it. So that was 13.1 and 13.2. 13.3, we're back to like how I normally do it. So hopefully it won't be too confusing. Anyway, have a great day.